Welcome to this video about A-level physics. We're looking at some mechanics and materials problems today. These are suitable for sort of year one, year two students. I'm going to try and go through as many as I can to help you out with your exam practice. So first one over here, we've got an exam question where we've got some cables and we're first of all asked to calculate the length of them. So the length of the cables, we have given the density, and in the question, we're also given the mass of the cables, both of them together, which is something to watch out for, and we're given their cross-sectional area. So the cross-section area is just of one of them. So to work out their length, we are going to need to first of all work out their volume. So volume equals mass divided by density. Now for the mass of just one of them, it says the mass of two is 3.7 times 10 to the power minus 10 to the power 4. So for the mass of one of them, we are going to have to divide that by 2 because they're identical. So we divide that by 2, then divide that by the density, which is 7.4 times 10 to the power 3. And that then gives us a volume of one of them of 2.5 meters cubed. Now, after the length, we should know that if we have cross-sectional area, because it's a cylinder, we know that the volume is going to be equal to the area times by the length of one of them. So the length of them is going to be equal to the volume divided by a cross-sectional area, which is what we just found out, 2.5 over the cross-sectional area, 9.6 times 10 to the power minus 3. If we do that, it gives us an answer of 260.4166, etc. Okay, so 260 here, because everything's to two significant figures, we can leave it as 260 meters. So for the next one, we're asked to work out the initial acceleration of a load. We're given the maximum tension in each cable, and we're given the mass of the load. We've also got to include the mass of the cables from earlier because they're not massless. We do have to consider that. And this question seems relatively straightforward. It's worth 4 marks. That's usually an indication you've got to do quite a bit of workings out to get to our correct answer. So to sort of imagine what's going on here, so we've got the cables down here, we've got the load here. We know the load's got a weight, and we've got the weight of the cables. So obviously weight equals mg. And we also know tension of the cable is going to act upwards. So we've got T from that cable and T from that cable. So we're going to have to sort of resolve those two forces and then equate them to basically F equals ma. So if our resultant force, we're going to have to say it's equal to, because it's accelerating upwards, because we know it says it's at its lowest point and it's accelerating back upwards. We can resolve these forces T minus mg, or T minus the weight. So that's our resultant force. So let's work that out then. So we've got T minus mg is going to be equal to 2 times the tension, because the tension in each cable is 1.6 times 10 to the power 6. So we've got that times by 2. Then we've got minus, and this isn't just the mass here, this is the mass of this plus the cables. So we've got 2.8 times 10 to the power 5 plus the cables, the mass of both of them together is 3.7 times 10 to the power 4 times by g. So that gives us our overall resultant force of 90230 newtons. So that's the resultant force. And we need to put that into F equals ma. So 90230. And again, this is the total mass. So total mass is going to be 2.8 times 10 to the 5 plus 3.7 times 10 to the 4. And then the acceleration is what we're trying to find out. So if we do 90230 divided by that, we should get overall our acceleration of the whole thing. And I've got 0.284 for mine. It does allow 0.29 as well. I think that's because of rounding. But yeah, that's what the how to calculate the acceleration for that question. This next bit of the question is all about safety. So it tells us for safety, the braking stress of each steel cable must be at least 3 times the maximum stress. This bit's important, don't miss that out. During the initial acceleration, it tells us the braking stress for steel is going to be equal to 890 megapascals. So what we need to do is to work out the stress in what's happening there, what's the stress going to be in each cable, and then compare it to this answer. Obviously times it by 3 as well. So stress is equal to force per unit area, or for tensile force applied per cross-sectional area. Now, the force we know, so this is just the tension we're looking at here, not resultant force. The tension is going to be in each cable 1.6 times 10 to the power 6. Cross-sectional area is up here, 9.6 times 10 to the power minus 3. That gives us a tension of 1.666, sort of rounded to 7 times by 10 to the power 8. which, if we think about megapascals, that's going to be 167 megapascals. So what we then got to do, it says the breaking stress must be at least 3 times that. So we'd say, okay, well, 3 times 167 megapascals is still significantly lower than 890 megapascals, as stated in the question. So it says the juice fluid operates safely. So we could say it therefore operates safely. Okay, this question was really poorly answered, this part D of this question, when this paper came out. There's a lot of information, so let's just spend a second going through what's actually going on here. So the village, there's a storage system, which we've been looking at earlier in the question, says combines it with a wind turbine to provide energy, shows how the output of the wind turbine varies. And then we've also got the power demand of the village. Now, let's keep an eye on these two. I'm going to color code them here. So the demand of the village, I'm going to put in red. That's this dotted thing here. And then we've also got the wind turbine, which I'm going to put in green so we can keep track on which one's which. The question later on is only asking us about one part of the graph, which is between 10 to 2. So we're only looking at this bit here for this question. It says when the power demand is greater than the output of the wind turbine, the load descends and generates electricity to match the demand. When it's fully descended, power is provided. The efficiency is 85%, and it says the maximum energy stored is 760 megajoules. So then it says, will the storage system and wind turbine provide enough electrical energy provided for this period of time? So for this period of time, what we've got to do is look at how much energy the village needs above what it's got from the wind turbine. So to do that, we've got a power time graph. So power times time is equal to energy. So we can find the area between these two. And that tells us the area under the red line is going to be the energy that the village needs. And the gap between them is going to be the bit that's not provided by the wind turbine. Wind turbine provides this amount, it's not going to provide this bit here. So essentially, is this village storage system going to provide enough to make up for that? So let's work out the area then. I'm going to do it up here just so it's all on one page. So the area is going to be equal to, and we can do a bit of estimation here. We can work out triangles if we want to. But basically, if we add up the squares, so we've got one big square there, pretty much half one there, half one there, and I reckon another half down here. We could say it's equal to 2.5 squares. You could work out the triangles, but I'd say that's a good enough estimation here. So 2.5 squares. Now we've got some unusual units here because we've got kilowatts and we've got hours. This is obviously in hours down our bottom. So 2.5, we know that each square is going to be equal to 2 hours and it's equal to the y-axis is going to be equal to 50 kilowatts. So 2.5 times by each square is going to be equal to 2 hours times by 50 kilowatts, which is going to be equal to 250. And this is a valid unit. It's not doesn't come up in specifications that much anymore, but it's going to be kilowatt hours. Don't be too worried about that. It's kilowatt hours. All we need to do is kilowatt hours is to get it into watts and seconds, is to multiply it by 1,000 to get it into watts, and then also multiply it because it's per hour, and we're trying to get to per second. We're sort of dividing by a divide by 3,600. So that gives us what's going to be 9 times 10 to the power 11 joules, or we could say 900 megajoules. So that's the amount of energy needed by this storage system. So let's then compare it to what the storage system is providing and see if it can actually do it or not. So the maximum energy stored by the system is 760, and then that's at an efficiency of 85%. So the amount needed is that. You probably see already, but if I've got provided the 760 megajoules times by 0.85, that's only going to give us 646 megajoules provided. So that comparison deduces the storage system going to be able to basically say no, it's not able to provide it overall because of that was what's needed and that's what's being provided. Right, next up, we've got a helicopter, which we've got a solar panel supplying it. There's a bunch of information down here, and we're asked a few different questions about it. So the first one we're looking at, it says the gas moves the rotor blades that has a density of 0.02, and we're after how much mass moved per second. We're given the gas velocity, so the gas is traveling downwards at 17.2 meters per second, and we're given the radius of the cylinder of air, of the sort of column of air just below it. So in questions like this, It's really, really important. When we talk about every second, it's really important that we know for a cylinder, the length per second is the same thing as the velocity. So this is cross-sectional area. Now in a cylinder, if I'm trying to find the volume, that's going to be equal to the area times by the length. Because we're talking about per second, the length per second is basically meters per second, which is going to be equal to the velocity. So in this case, the length of the cylinder per second is going to be the velocity, so it's 17.2. So to work out our cross-section area times by our velocity will actually give us the volume per second, because it's going to be the length per second that we're working out as 17.2. So let's work that out over here because I've run out of room there. So we're first of all going to do volume. So cross-section area, we've got obviously radius is 0.6. So pi r squared times by v. So equal pi times by 0.6 squared times by 17.2. And that's going to give us 19.45. Then we're after the mass. That's what we're trying to find, the mass per second. So we've got mass equals density times volume. So 19.5, and that's going to be meters cubed per second, times by the density, which is in the question 0.00, which then gives us our mass of 0.389. And again, that's kilograms per second. So that's not disappeared. It's kind of tracked its way down. And that's very close to 0.4. Make sure you give it to more decimal places than they asked for. But that'll be enough for 3 marks in this question. Next, we're asked to find the mass of the helicopter. It says the movement of the gas creates an upward force on the helicopter. This upward force enables the helicopter to hover at constant height. Constant height means it's in equilibrium. That's why they're including that in the question, because we're going to have to use that to work out the forces on the helicopter. Tells us the gravitational field strength on Mars, so it's not on Earth, is 3.72, and we're asked to calculate the mass of the helicopter. So we know, if I were to draw the quick three-boy diagram here, this is my wonderful helicopter. When we've got, I should do that diagram there, shouldn't I? Anyway, we've got weight going downwards, which is obviously mg. The force upwards is provided by the upwards force on the helicopter. Now, the force upwards, a lot of people in this question, when I've marked it before, struggle to find out what that force is. So let's have a think. Earlier in the question, they asked us to show the mass per second that the helicopter moves. They never ask you to show anything unless they ask to use it later in the question. So we've got here the mass per second. So let me just write that in a sort of equation form. The mass per second, or the mass divided by time, is equal to 0.389, or you can use 0.4 if you want to. So how do I get that in a force? Well, if we look at our equation sheet, we know that force is equal to the change in momentum, or the mass times by the change in velocity over time. If we rewrite that slightly differently, we've got that is equal to mt times by v. So we've actually got these quantities already to find the force, because I know what mass over time is. We worked out earlier in kilograms per second, and we know what the velocity is, because that's just earlier on the question, 17.2. So let's work out that force and see if that can help us find the mass. So multiplying those values together, so we've got our 0.389 times by 17.2. We're going to have our overall force is therefore 6.6908 newtons. We said they're in equilibrium, so that means that that force is going to be equal to mg. So we don't know what the mass is, but we know that gravitational field strength is 3.72. So I've got mass equals the force I've just worked out divided by g. So 6.6908 divided by 3.72. That's g in this question. And that's going to give us overall mass of the helicopter of 1.7986, which we should do to a couple of significant figures, because down here we've got a couple of significant figures. So that's going to be 1.8 kilograms, which sounds reasonable for a helicopter you're going to put on Mars. So to finish off this question, it says the battery stores 0.035 kilowatt hours of energy before a flight. The time taken is 39 seconds. The battery has an output of 340 during the flight. We're asked to determine the percentage of the initial energy stored that is transferred. So the energy that's transferred is going to be our energy here. So it's provided by the power times time. And we have to convert this and sort of work these out as a percentage. So during the flight, we know the energy is going to be equal to power times time, which is 340 times by 39 seconds. Let's get marks for doing that straight away. So 340 times by 39 is 13260. And then the amount stored, so the stored energy is going to be equal to 0.035, and that's in kilowatt hours. So we times by 1,000, and because it's given in hours, we can then times by also 3,600 to get it into joules, because that's per second. So if we do 0.035 times by those two numbers, we are going to get 12600. Get an extra zero on there, I forgot about. So the percentage of basically this divided by this, so 13260 divided by 126,000 is then going to be, was it 10.5-ish%, which is going to give 11% because we've got two sig figs here, two sig figs here. So 11% is the correct two significant figures. Okay, to continue the question, and we've got a non-calculation question up here, which says the maximum flight time of a few minutes is limited due to the energy stored in the battery. The battery accounts for about 15% of the helicopter's mass. The student suggests that adding another identical battery will double the energy available and will also double its flight time. Without calculation, is the student correct? So it might seem like, yes, it would do, because it would have double the energy, which means it can have double the work done, it can travel double the distance. However, we are not considering the lift and the forces acting on the helicopter that we looked at earlier in the question. Now, it tells us up here 15% of the helicopter's mass. That's not insignificant, so we have to consider that as well. So basically, the student is not correct because of the mass that we've got to consider. So the mass will increase the weight of the whole thing, the helicopter. So we'd say the helicopter, to be able to overcome that, consider the forces on it, must have to provide a greater lift to be able to lift the whole thing off the ground. So to be able to do that, to be able to increase the lift force, because the weight has increased, it's going to need to displace more air, which means basically it's going to need to do more work. So it will need to displace more air. And we say to do that, blade spin faster, and therefore so more work must be done each second. So even though it's taking an extra battery on board, by providing extra mass, it's then needing even more energy. So double wouldn't be enough to account for that. Okay, let's do a little bit of SUVAT to work out these two questions. So again, some information down here. It says the helicopter takes off. Its blades stop turning when it gets to this point here. It's got an upwards velocity of 0.55 meters per second. We're given the gravitational field strength on Mars. So let's do a bit of SUVAT to work this out. So in each of these equations, we are trying to work out the S this time, which is H. Its initial velocity is 0 because it's taken off from the surface. Its final velocity is 5.5. A acceleration due to gravity is the same thing as gravitational field strength, so 3.72, and we're trying to find the height. So the equation we could use is V equals U plus AT, and we know V is not 5.5, 0.55, so 0.55 equals nothing plus 3.72 multiplied by the time. So therefore time is going to be equal to 0.55 over 3.72, which can be equal to 0.1478, blah, blah, blah. Going to give it to two sig figs because we've got a lot of two significant figures in the question. So 0.15. Next one, we've got the helicopter making contact with the surface, has a velocity of 2.2 seconds. So it stops going upwards and it's going to kind of crash back down to the surface over here with a velocity when it gets to this point of 2.2. So let's do SUVAT again. So we're trying to find, this time we didn't know what the height was originally, but we're trying to find it in this question. U this time is going to be positive 0.55. We consider it's going the upwards direction. The velocity as it comes down is going to be minus 2.2. Now, these positive negatives aren't actually relevant for this question, but it's always good to put them in regardless. The time we do know, 0.15, is usually better not to use your previous values you've worked out unless it's a show question, just in case you get them wrong. It's harder for a marker to see like where you are. As those show your calculations correctly, it should be obvious. So we're trying to find S here. The ones we know are U, V, and A. So I'm going to use V squared equals u squared plus 2as and try and find s. So we know the initial velocity is going 0.55. So again, this is why the signs don't matter because we're squaring them anyway. So 2.2 squared plus 2 times by 3.72 times by s, or the height, I'm going to call it here. So then we do 2.2 squared minus 0.55 squared, and then divide the whole thing by 2 lots of 3.72. And if we do all that, we should get a height of 0.6098, etc., which again will do to 2 sig figs, which is 0.61 meters, which sounds reasonable for our drone. And lastly, for this question, it says a student suggests that the acceleration of the helicopter is constant from the instant the blades stop rotating until it comes back down to the surface. Discuss this suggestion with reference to an appropriate law of Newton's law of motion. So when it says discuss, what it means is figure out are they right or wrong, and then explain why. So the student here is correct. I'll explain why. As the helicopter comes back down to the surface, if the helicopter blades are not spinning, the only force that they've got acting on them is their weight. The helicopter blades aren't spinning, they no longer have an upwards force. So the reason it's correct is because weight is the only force acting. So the only force, which is meaning the resultant force downwards. Now Newton's second law, Newton's law of motion, one we're going to look at is F equals ma. If the only resultant force is the weight going downwards and the mass of the thing is constant, that means that they're going to experience an acceleration that's constant. So the force, weight is the only force acting. So we'd say this is constant and the mass is constant. So due to F equals ma, acceleration can't change or must be constant too. There we go. Long old question, that whole one. But that's the helicopter one with lots of different variety of forces, topics, and mechanics topics in there. Okay, this question is a lot about materials and a bit about moments and mechanics as well. The first bit, we're asked to work out the Young modulus of the metal. Now, the metal we should know for metals, there is an initial straight part to the graph, which is up to the limit of proportionality. Then it starts to bend. To work out the Young modulus, we're only looking at the straight bit. So grab a ruler and put it up to the line and then do it basically up to where you're convinced it's being straight. So I'm just going to go to here. As long as you're using a sizable, like more than half of the line, just do a part that makes it easier for you. So I've just done up to a line here, and I'm going to go along, and this is going to be my stress on this axis. So I've got 105 megapascals. That's my change in Y, and I've got up here, this is 7.5 times 10 to the minus 4. That's what it says on the graph down here. So to find the Young modulus, we just need to divide those two answers, which is going to give us 105 times 10 to the 6 over 7.5 times 10 to the minus 4, which is going to be 1.40 times 10 to the 11, which it's in pascals, so we can leave it in regular units like that. Next question is to show how this, explain how the graph shows this metal is brittle. So it tells you in the question that it fractures. So it says it's given stress up to the point it fractures. So basically, there's no more graph after this bit. The whole thing is broken. So the idea is for something that's brittle means it's going to have very little strain or very little extension before it breaks. So we'd say something like there is very little strain before it fractures or before the fracture point. And we can't say there's no increase in strain because it definitely does curve off a little bit here, but before it fractures, I should say, down here. And that'll be enough for the mark with this question. Okay, next this question gets a bit tricky. We've got two beams, which it says down here are two identical steel wires, and they're rigid. They're held up with some supports from a ceiling. They've got a bar between them, and they've got a lamp here, which is halfway along. So this information is used for two questions. First of all, we're asked to calculate the extension in the wire, and later on we're going to ask to work out something else when the lamp moves. So for the extension in the wire, let's look at what values we've got already. So we've got Young modulus of steel, the thing we're using, that's good. Got diameter, which means we can find area from that with pi r squared or pi d squared over 4. And then we also know the distance between the wires. That's not particularly relevant here. We know the lamp is halfway along. And we do need to know these two here, which is the mass of the bar between them, or the beam between them, and the mass of the lamp. So what we're going to do to work out the extension, we're going to use the Young modulus equation. So this is one of the very few sort of equations you're not given. You do have to sort of derive it from the idea that Young modulus equals stress over strain. And we know stress is force over area, strain is delta L, change in length divided by original length. And if you make that simpler, you're going to have F over L divided by delta L times by area. So that's what Young modulus is equal to. So I'm going to write that down here. So FL over L delta L. Getting confused my L's here. Okay, so we're trying to find the extension. So let's rearrange that one more time. So delta L, we just switch places with the Young modulus. So force times by length divided by Young modulus times by cross-sectional area. Now, the tricky bit here is the force because we're not told the force. So for the force in total, we are told that the mass of AB, so that thing there, and the lamp. So we then work out, we've got 4.4 plus 16 times pi g to work out the weight. So we're going to do so 20.4 times by 9.81. Then that's the total. So the force for one beam is just going to be that divided by 2, because there's 2 beams that each have half a force. So that's going to give us 981.6 newtons. So that's for just one of these. Apparently, I can't type into a calculator. Try that again. That's 100.062 or 100 newtons. That's for each. Well, we're only after the extension of each wire, so we can leave it in terms of that. So next we've got extension is then that. So I'm just going to round it to 100 times by the length, which it tells us is 1.2. The Young modulus is 2.1 times 10 to the 11. Cross-section area, we're going to do pi times by, and be careful with millimeters here. This is 0.0004 squared, or pi d squared over 4. If we put all that in, we're going to get an extension of 1.14 times 10 to the minus 3, which sounds reasonable because that's about 1.14 millimeters. So that's the extension for each of them. Okay, this question to finish off is a whopping 5 marks, and we've got to work out a distance. The lamp is not necessarily longer in the center anymore, and we've got to change one of the aluminium wires instead of a steel wire. Everything else is the same. It gives us the new Young modulus of aluminium, and we're asked to determine the distance along which this would still be horizontal. Tells us down here, we've got the aluminium wire has the a slightly bigger diameter, so this is now 1.6 millimeters instead of 0.8. It says the unloaded length of aluminium wire is the same as the original, and the lamp is at the midpoint. One extends more than the other, so therefore has to move to make it horizontal. So this is a really tricky question, okay? We are going to do moments at the end, but first of all, we're going to have to work out the forces because to take moments, we need to know forces, and we don't know what they are at the moment. So let's work those out first, and then we're going to take some moments. So first thing to say is that tells you unloaded is the same, and we've got to look at the extension. So the extension for each, because they're horizontal, it means they have to have extended by the same amount. Okay, they're the same length originally. Whatever this is, they've got extended by the same amount on each side. So that's the key thing here, is to note the same extension for both. So both for aluminium and steel. Okay, so aluminium was B, steel was A. So how we then use that is to use our equation from earlier. So extension equals FL over Young modulus times area, and use that for both. So we know, I'm just going to write down again here to keep track of everything. So basically, the force of the steel wire times by the original length divided by the Young modulus of the steel wire times by cross-section area has to equal the force of that aluminium wire times by its original length divided by Young modulus of the aluminium times by its cross-sectional area as well. Now, this still looks pretty horrible, but we can make it a little bit simpler for ourselves. We said earlier in the question that the unloaded length is the same, so the original length is the same, so we can ignore L. And we also know if cross-sectional area, obviously it's pi r squared. Pi is the same on both sides, it's just the r that's different. So effectively, instead of A, we can just put r squared. Of course, I had the wrong one there. We could put r squared instead of that one. And then we've got basically a ratios question. So we don't know what the forces are yet. That's what we're trying to find out, the difference, the ratio between the forces. So we've got AL and steel. Now we know that the Young modulus of our steel is given to us, where's it gone, 2.1. So I'm just going to put these numbers in now so we can figure out what we're doing. So I'm going to say, 2.1, I'm going to leave it in same form as it is there. And on this side, this is given to us in power of 10, which I know is a bit confusing. So I'm just going to say it's 0.7 times 10 to the 11, because that's basically the same thing. We've got to keep those two consistent. And we said area earlier, we could just say, because pi is the same on both sides, we can say it's equal to r squared. So therefore, for our steel, we're going to have, and I'm just going to leave it in millimeters, doesn't matter because it's a ratio sort of question. It's given to us 8 millimeters, so I'm just going to say 8 squared over there. And then on the right-hand side, actually I'll say 0.8 because that's how it's given to us. Right-hand side, it says the new diameter is 1.6. So I'm going to say 1.6 squared over there. So I'm going to totally bypass this bit here because there's a lot of workings to this question. So let's then just simplify this down a little bit. So we've got Fs divided by, so 2.1 times by 0.8 squared, which is going to give us F over 1.344. It's going to be equal to F of aluminium over, and now I've got 0.7 times by 1.6 squared, which is going to be F over 1.792. So we're going to simplify this down even further. Yeah, I can simplify this a little bit, just crunch numbers down a bit and come to, so 4 over 3 or 1.33 times by the force of steel is equal to the force of aluminium is equal to the force on steel. Right, almost there. Okay. Now we know that both of these forces acting downwards are going to be equal to the weight of the lamp plus the weight of the beam. And we said earlier in the question that was equal to 200 because we worked out here. We said it's 100 per steel cable. So I've got 100 there, 100 there, and that's the same thing here. Okay. So therefore we've got 1.33 lots of the aluminium plus the steel is going to be equal to 200 newtons. Okay, so how do we work this out then? So effectively, we've got a ratios question here. Now, I probably should have left this in ratios earlier, probably makes it a bit easier. 1.33 is the same as 4 over 3. It's because basically we've got to split 200 newtons into ratios. So I've got basically 4 over 3 here. This one is 3 over 4. So basically if I split 200, and you probably have a better way of doing this in A-level maths, but to ratios, so we got 4 over 3, we've got 3 over 4. So therefore, I've got 7 parts total. So 200 divided by 7. And then for each one of these, we can times by basically 200 over 7 gives us 7 parts. And then we've got to then times by 4 for this one and 3 for this one, essentially. So let me do that quickly. So that gives us, if I've got the 4 sevenths, that's going to give us 114. And that's for aluminium. And then we've got times by 3 sevenths. Go off the screen here. That's going to give us 86. And that's going to be for our steel, which it was originally. Okay. So, goodness me, right. Loads of work for this one. Those are our two forces. I did say it'd take a long time, and then we've got to work out moments. Okay. But this bit, I promise you, is not awful. So we're going to treat A as the pivot point. So A is our pivot point. So let's do, first of all, clockwise moments. So I've got the lamp, which I know its mass, so therefore I know its weight, which is 16. And we don't know how far away it is, so I'm going to say 16g times by x, because we don't know what that is. And we've also got the center of mass. Don't miss out this bit. Center of mass of the beam is going to be 1 meter away from the pivot we're using. And we do know its mass. We know it's 4.4 g. And it's 1 meter away, so therefore it's put it in there just for completeness, but we don't need to worry too much about distance. And that's then going to equal our anti-clockwise moments. So our anti-clockwise moments are going to be what our newly calculated force, that's absolutely forever, which is the aluminium wire up here, which we said was 114. So 114, and that's 2 meters away from the other end. So let's make life a bit simpler. So 16g times x is going to be equal to, what was that, 228 minus 4.4g. And obviously, if you sub in values for g, we've got 16 times by 9.81 equals, and I've got 228 minus 4.4g, which is going to give us 184.836. And then finally, so to work out x, we've got to do x equals that, divide by 16g. I've just got a paper at the end to fit it all in. X will then equal 1.1 775, etc., which round to two sig figs is 1.18 meters, which is what we put in the answer line. What an incredible question. 1.18 meters. A lot of work. It's 5 marks, but that's how you do it. Okay, people, hope you found that useful. That question was a bit of a slog. Not sure if there's a quicker way of doing it. It's just one of those ones you've got to spend a bit of time on, A-level physics questions. Let me know if you want to do another topic, essentially from maybe year 2 coming up next, and please leave a like if you found it really useful.